In this presentation, team, are going to do introduction to graphs. We are going to do the introduction to graphs. So these are the objectives of this chapter. So by the end of this unit, you should be able to identify different types of graphs, also elaborate the concept of graphs as well as the terminologies related to graph theory. I was trying to add someone here. Let's make sure that we all join earlier. Let's make sure that we all join earlier. If the meeting is scheduled to start at exactly 1300, make sure that by 1300 you are already in the meeting. So let's talk about graphs. What are graphs in general? So a graph is a non-empty set of points called vertices and a set of line segments joining pairs of vertices called edges. So in graphs, we'll be talking about these two sets, and they must be a non-empty set, which is we must have a set of vertices and a set of edges. We need two of these sets to form a graph. So our graph will be a set of V, which is edges, which is vertices, and then another set of E, which will be a set of what? Of edges. So formally a graph G consists of two finite sets, which is a set V, which will be a set of G, or a set of vertices, or points, or nodes. And then we've got a set E, which is E of G, which will be a set of what? Of edges. So where each edge corresponds to a pair of vertices, which means we need a pair of vertices, and then we have a what? A single edge there, or other edges there. Maybe it will be two or one bidirectional or so. So like here, we've got this V1, V2, V3, V4, V5 is our vertices, and we've got these E1, E2, E3, E4, E5, E6 is our edges. So the graph G, we are referring to this graph. So a graph G with the V of G, V1, V2, V3, V4, V5, and E of G, which are our edges, E1, E2, E3, E4, E5, and then E6. So this one is what we call a what? A graph. We've got a set of edges and a set of vertices. I don't know if there is any question here. So I think I can actually move to the next slide. So let's talk about the terminology that we use in a graphs. Okay. So any edge connects either one or two vertices is called its endpoints. Edge 1 connects vertex V1 and V2 described as V1, V2. That is V1 and V2 are the endpoints of any edge E1. We are saying if you have, like here, we've got V1 and V2 as an endpoint of edge 1 here. So an edge which will be connecting V1 and V2 have got an endpoint of these vertices and these vertices. So an edge with just one endpoint is called a what? A loop. So this one is an edge. E1 is an edge, but there's what we call a loop. A loop is also an edge, but it only have a single endpoint. Like here, it starts at V3 and ends at V3. So it's a loop. It's like it is going out as an out degree and then going back as an in degree at V3. So So two vertices that are connected by an edge are called adjacent. And a vertex that is an endpoint of a loop is said to be adjacent to itself. So when you are talking of adjacent vertices, there will be an edge that will be linking those vertices. Like you have got, let's say this one V4 and this V2. So V2 is adjacent to V4 because we have got this edge E4, which is joining them. So they are adjacent to each other. But also there is a vertex which will be adjacent to itself. Whenever there is a loop, we say that it is adjacent to itself, like the V3 is adjacent to itself since it is actually linked to itself. Don't think there's more explanation there. So let's talk about an edge is said to be incident on each of its endpoints. That is, E1 is incident on V1 and V2. Like here, E1 is incident here and here, both it's bidirectional. It's silent about the direction also. So it's going here as well as going here. So it's incident to V1 and V2. Also, a vertex on which no edges are incident is called isolated. We can have also isolated vertices or isolated vertex on our graph. Like here, we've got this V5 is an isolated vertex. Why? Because there is no any other vertex which is adjacent to it or connected to it or linked to it. That's an isolated vertex. Two distinct edges with the same set of endpoints are said to be parallel. That is E2 and E3. We've got E2 and E3. These ones are parallel. Why? Because they have got the same start point and the same end point. Somewhere. Their endpoints are all the same. So they are parallel. You can go this way or you can go this way. Or you can go this way or you can go this way. So they are parallel edges. I don't know if there is any question here. Okay, there's no hand, so I think I can move on. So let's talk about the types of graphs. Let's talk about these types of graphs. We have what we call a directed graph. So definition, a directed graph or a digraph. These things can be used interchangeably. If you are being asked of a digraph, you are being asked for a directed graph. So a directed graph or a digraph, G, consists of a set V of vertices and a set E of edges, such that each edge E of E is an element of E is associated with an ordered pair of vertices. It's like there will be a directional. If we have got this vertex and this vertex V2, and then we have got a link here, it will be clearly stating that the order of this pairs, like we are coming from V1 to V2. That's a directed graph. So a directed graph is shown in the fig 6.3. The directed edges are indicated by arrows. Here, the directed edges are indicated by arrows. That is, edge E1 is associated with the ordered pair A, B, like here. This edge E1 is associated with what? With ordered pair A, B. Like we are moving from A to B. And the edge E2 is associated with the ordered pairs C, D of vertices. Like here, E2, where is E2? E2 is here. So we are moving from D to C. So it will be DC. Here, I think it's DC on E2. Because we are moving from D to C. So this one is actually an error here. That's what we say about the directed graphs. There will be a direction on your edge. On all of your edges, there will be a direction or a directional arrow there. And then let's talk about the symbol graphs. We have what we call a symbol graph. So a graph with neither loops nor parallel edges is called a symbol graph. So for a graph to be a symbol graph, it must not have a loop as well as parallel edges, those edges with the same endpoints, as well as those loops where on a vertex you have an edge that will be going out as well as come back to that edge, to that vertex. Like if we have a vertex V1, then we have a loop, an edge which will be actually going out, then came back in at the same vertex. So example, since the graph below has neither parallel edges nor loops, it is a simple graph. Here, we do not have any loop, and also we do not have any parallel edges. Like here, if we're going to have another edge, which will be actually parallel to W1, it will be not a simple graph. I think I can move on to the issue of weighted graph. With what we call a weighted graph. So a graph with the numbers on the edges or weight on the edges is called a weighted graph. So if edge E is labeled K, we say that the weight of edge E is what? Is K. Like you've got this edge AB or BA, because it's not actually a directed graph. You cannot tell is it AB or BA. But this edge have got a weight of 8. This one have got a weight of 9. So that's a weighted graph. All of its edges or some of its edges will be actually having a what? A weight assigned to those edges. So that's what makes it a weighted graph. Don't know if there is any question. Is there any question?
No, sir.
It's fine. Think I can continue. Let's talk about a complete graph. You need to know what a complete graph is. So a complete graph on any vertices, if you have any vertices, is a simple graph. So first, a complete graph is a simple graph. So is a simple graph in which each vertex is connected to every other vertex and is denoted by Kn, where Kn means that there are any vertices. N will be representing your vertex. So in other words, all your vertices must be connected, or there are no isolated vertices. So the following are complete graphs K1, K2, and K3. We've got this graph K1. This one on its own is a complete graph. Why? Because this vertex is actually joined or are connected to itself. Then we've got this one with the two vertices. This vertex connected to this vertices, or the other way. So which means this one is a complete graph, and it's also a simple graph. There are no parallel edges, there are no loops. So it's a simple graph, and then all vertices are also connected, then it's a what? It's a complete graph. Also this one, it's a complete graph. Why? Because first it's a simple graph, and then all vertices are connected, and then there are no parallel, there are no loops, and there are no parallel edges there. So it's a what? It's a complete graph. So whenever you're talking of a complete graph, you need to think about these conditions: a simple graph, and also each in which each vertex is connected to every other vertex. So if you are here, you must have a way of going to this vertex. It's either you're going this way or you're going this way, something like that. If you touch any vertex, you must have a way to reach to all other vertices. That's a complete graph. So now let's talk about cycles. Let's talk about cycles. So a cycle graph is a graph that consists of a single cycle, or in other words, some number of vertices, at least 3, if the graph is simple, connected in a closed chain. That's a cycle. It's like your graph will be having vertices that will be connected in a closed chain, which will make it a cycle. If I start here, I can also come back here through this way, this way, this way. That's a cycle graph. Like here, you can start from here, going this way, this way, this way. You can do the same here, you can go this way, this way, this way, this way. So that's a cycle graph. Don't know if there are questions here. If there's no hint, can actually talk about the n-cube graph. And n-cube graph. This one you need to understand the binary system as well as the n-cube. For you to understand this easily, you need to understand the binary system. How does it work, or so something like that? So the n-cube denoted by Qn is a graph that has vertices representing the 2 to the power n bit strings of length n, which means your n here will be the length of your bit string. Or a bit string, it will be a string of zeros and ones, right? So the two vertices are adjacent if and only if the bit strings that they represent differ in exactly 1 bit position. Like if you are talking of 1, 2, 3, 4. So this one will be adjacent to this one. This one is also adjacent to this one. This one is also adjacent to this one, because there is a 1 bit. They will be actually differ by just exactly 1 bit position if we convert these ones to binary. So you need to just to understand all those conditions for your n-cube. Firstly is 2 to the power n for your bit string, and then your n will be the length of your bit string, and then you need to know that they will be actually, your vertex will be actually adjacent to the one which is actually exactly 1 bit position from the actual vertex that we'll be talking about, that we'll be referencing to. So the n-cube Qn with n is equal to 1, 2, and 3 are shown below. Like here we have got our n is 1. We have got 2 to the power 1 here. We are using this one to generate our cube, which will be 2 to the power 1, because our n will be equal to 1. So whenever you have 2 to the power 1, you know that your bit string, or the combination of zeros and 1, will be of length 1, which means you'll be having either a 1 are a 0 or a 1. So in decimal, we'll be talking about of 0 and 1 here. Like in decimal, like 0, 1, 2, 3. In decimal, in base 10, we'll be talking of 0 and 1. So 0 in binary is 0 and 1 in binary is what? It's 1. So we'll be talking of vertices 0 and 1. And then you connect them because they are adjacent. Why? Because they differ by just a single, by just exactly 1 bit position. Here it's 0 and then it's 1. So this is how do you generate this graph Q1. Let's talk about this cube Q2, which you'll be actually using 2 to the power 2. Was here our bit string or n, our bit string length or n will be 2. So we'll be talking of, let me just rub here so that I demonstrate the concept. Let me, maybe I will give the area to use. Okay, so here we are talking of 2 to the power 2, right? Which will be equal to what? To 4, which means we need 4 vertices. But these vertices must be differ by 1 bit position. So we are talking of 0, 1, 2, 3, 4 vertices, like in decimal. So you need this one 0 to be in binary, 1 to be in binary, 2 in binary, 3 in binary, 4 in binary. So we'll be talking about bit string. So we need to convert these numbers to binary, and also it must be of 2, the length. Here for 0, here it will be 0, 0. Then for 1, it will be 0, 1. Because we need the bit string of length 2 here, because that's our n. So you'll be having 0, 0, 0, 1, and then we have got a 1, 1 and a 1, 0 here. So it will be 0, 1, 2, 3, 4. It will be 0, 1, 2, 3, not up to 4, sorry. We need 1, 2, 1, 2, 3, 4. These ones is the ones that we actually want here. So how do you connect them? You connect them using this principle. They must be differ in a position by just, they must differ in exactly 1 bit position. So this is why you link this one and then this one with this one, this one, this one, and this one with this one. So this will be the result of 2 to the power 3 or that any cube. This will be your result. Then you can talk of Q3. This one, where your n will be equal to 3. So when your n is equal to 3, let me erase everything. We are talking of n be equal to 3, so we'll be talking of 2 to the power 3, which will be equal to 8. So we need a bit string of length 3, right? Which means your, and then we need 8 vertices. So your vertex will be 0 up to like 7, 0, 1, 2, 3, 4, 5, 6, 7 or so. So you need to convert those numbers so that they will be in binary, in its binary representation, but is a 3-bit string. Its length will be 3. So for 1, it will be, for 0, it will be 0, 0, 0, and then 0, 0, 1, 0, 1, 0, just going on like that. So later you join all your vertices to form this cube. Just like that. You are adding from this cube, you are adding this vertex 1, 1, 0 here as another point, then this 1, 1 is another point, and then you add the 1, 1, 0 that we have here, and you add another one here, 0, 0, 1, and then you join them just like this. Join them, join them, join them, join them. I don't know if I've done it correctly. Yeah, something like this. Then you come up with this cube. But only that here you are using 3-bit string. Our length the length of these bit strings will be 3. So here we'll be adding a 0, something like that. Here it will be 001. I don't know if there is any question here. Is there any question? So if you are silent and there's no hand, I think you can talk of a bipartite graph. Let's talk of a bipartite graph. I'm trying to add someone. Let's talk of a bipartite graph. So a graph G with V and E is bipartite if there exist subset V1 and V2 of V such that V1 intersecting V2 will be equal to empty set, or will be equal to, it will be an empty set, and V1 union V2 will be equal to the original V, and each edge in E is incident on one vertex in V1 and one vertex in V2. That's what we call a bipartite graph. And then we have got this example. I will explain this definition on this example. So we've got this example, we've got the graph in Fig 6.10 is a bipartite, since if we let V1 and V2 be this and this, so each edge is incident on one vertex. So what we are saying here, team, is that we've got a graph G with a set of vertices and a set of edges. So for it to be a bipartite, you need to divide, you must be able to divide a set of vertices into two sets. And then when you divide those, like here, we've got a set, we've got this graph with the vertices V1, V2, V3, V4, V5. They are all vertices. These vertices, we have managed to divide them into two sets. We've got this set on this side, we've got this set and this set, just like this. You manage to create two sets, and these two sets must satisfy these two conditions. Just like we must not have V1 intersecting V2, which means it must be an empty set. What we are saying is that we must not have the any of the edges, any of the vertices here connecting to some of the vertices in this set, as well as this side. We must not have any of the vertices connecting to this one, like V4 connecting to V5. And also V1 union V2 must be equal to the original V. What we are saying is that if you take V1, V2, V3, V4, V and 5, V5 and V5, they must all constitute the original set of vertices. Like here we're having the set of vertices as V1, V2, V3, V4, V5. So we must ensure that they are all covered in these two sets. So those are the conditions for a bipartite graph. So we need to check if this one is a bipartite graph. Yes, it is a bipartite graph. Why? Because in this part, or in this set that we've actually created, maybe let's say this one is our V1 and this one is our V2, right? There are no edges which are connecting the elements in this set, as well as this side. And also here, each edge in E is incident on one vertex in V1 and one vertex in V2. Like here, this one is connected to something on this side, and this one is also connected to something on this side, and this one is also connected to something on this side. So those are the conditions that you need for a bipartite graph. Each and every element on this side must be also connected to something on this side. Also, like here, we must have an element connected to something on this side. I don't know if there is any question before we move on the bipartite graphs. Is all clear? It's fine. I think let's move on. There's this example. The graph below is not a bipartite. We are talking of this graph. It's not a bipartite graph. Why? It is often easier to prove that a graph is not a bipartite by arguing by contradiction. We are going to choose the proof by contradiction to prove if this graph is bipartite or not. Suppose that the graph in fig 6.11 is bipartite. We suppose that it is a bipartite graph at first, and then we must prove that it is a bipartite graph. Otherwise, it will lead to a what? To a contradiction. Then we say that this one is not a what? It's not a bipartite graph. That's the method of printing by of proving by what? By contradiction. So then the vertex set can be partitioned into two subsets like V1 and V2. We need to partition these vertices into V1 and the capital V2, right? That each edge is incident to one on such that each edge is incident one on vertex in and one on vertex in V2. Like you need to create two sets. Maybe you can say like this one V3 is instead of V1, so they must be in two different sets, like V3 in the large V1 and this one in capital V2, something like that. So yes, since V4 and V5 are adjacent, now consider the vertices V4, V5, and V6. We are just taking this symbol, V4. Let me just erase all these. So here we've got, we are taking V4. Where's V4? This one, we are taking V4, V5, and V6. We are just taking these vertices. Right? So since V4 and V5 are adjacent, V4, this one and this one are adjacent. One is in V1 and the other is in V2. So we are saying we've got V1 here and V2 here as our states here, as our states. So we'll be saying we'll be saying since V4 and V5 are adjacent, one is in V1, we can say maybe V4 is in V1 and then V5 is in V2. So they are adjacent, so we put a line connecting them, right? And then we may assume that V4 is an element of V1 and that V5 is the element of V2. So since V5 and V6 are adjacent, here we have got V5 and V6. They are also adjacent. So V5 must be and is an element of what? Of V2, right? And V6 is an element of V1. V6 here will be an element of V1 because they are also what? Adjacent, right? And we've already V5 in V2, so we cannot place a V5 here. So we can put a line here. But since V4 and V6 here, V4 and V6 are also adjacent, and V4 is an element of V1, so V6 will be also an element of V2 here. So you see, we'll be ending up having V6 here and V6 here. So, but now V6 is an element of V1 and an element of V2, which is a contradiction since V1 and V2 are disjoint sets. Therefore, the graph in Fig 6.1.1 is not a bipartite graph. Since we said that the intersection of these two must be an empty set, so if we are going to have a V6 here, we'll be having something on our intersection. So this one is not a what? It's not a bipartite graph. I don't know if there is any question here. Is there
No,
any
sir.
question? Okay,
No,
it's
sir.
fine. It's fine. So let's talk of a complete bipartite graph. What are a complete bipartite graph? So the complete bipartite graph on M and N vertices denoted by K, M, N is the simple graph, is a simple graph whose vertex set is partitioned into two sets, V1 with M vertices and V2 with N vertices, in which these are edges between each pair of V1, V2, where V1 is in V1 and V2 is in V2. A complete bipartite graph team is just different from other bipartite graph in the sense that all the vertices in here must be connected to each and every vertex on the other set. Like here, if this one is our V1 and this one is our V2, like this, all these, this one must be connected to this, connected to this, to this, to this, as well as this one must be connected to this, then this, then this, then this one as well. So all these vertices must be connected to all these vertices. So that's a complete bipartite graph. Like if we have something like this is our V1, this is our V2, then maybe let me see a color that can work here. Maybe we've got this one and this and this. And then we have this two here. So for it to be a complete bipartite graph, this one must be linked to this and this, and also this one must be linked to this as well as this one. Also, this one must be linked to this vertex and this vertex to make it a complete bipartite graph. I don't know if there is any question here. Is there any question? It's fine. I think we can move on to a subgraph. So this is all about, this is just the terminology that we use in a graph theory, as well as the types of graphs that we have in a graph theory, so that when you actually dive deep into graph theory, we will actually not run in these problems of not to know what a subgraph is, what a cycle, what a loop, or so something like that. So sometimes we need to consider only a part for a subgraph. Sometimes we need to consider only a part of a graph, right? So for example, if we have a large computer network, we may need to analyze only a small part of the network in order to solve a certain problem. So a subgraph G prime can be obtained by selecting certain edges and vertices from a graph of G, subject to the restriction that if we select an edge in G that is incident on vertices V and W, we must include V and W in G prime. That's what will be an idea of a subgraph. We are saying from this network, we need this part of the graph. So we'll be actually in this node or this user and this user and this user on this part of a network, something like that from that part of a network. We need to consider just maybe 5 users from 10 users. So definition, let G be a graph with the V and E. So we call V prime and E prime a subgraph of G. If V prime is a subset of V and E prime is a subset of E, and then B, for every edge, E prime is an element of E prime. If E prime is incident on V prime and VW, then V prime and W prime are element of V prime. What you are trying to say here, Tim, is that whenever you have a graph, maybe let me say I have got this vertex and this one, and this one here, and then I have this one edge and this edge and this edge. Maybe this one is a V, maybe it's a V1, V2, V3 here. I can actually have a subgraph here, just like this, which will be V1 here and here V2. It's a subgraph. Why? Because V1 and V2 are subset of our vertices or large V, which will be consisting of V1, V2, and V3. And we've got this edge, which is an incident to V1 and V2. This edge here, you see, is common, is also here. Maybe you can name it E prime or E1 or just E2 or something like that. So this one will be our subgraph of this graph. This will be the original graph, and this one will be our subgraph. I don't know if there is any question here. So here I've got an example of a subgraph. So we've got the graph G prime, which have got V prime and E prime. I was saying G prime or graph G prime is a subgraph of the graph G. Since V prime is a subset or is a proper subset of V, and E prime is a proper subset of what? Of E. So, like this one, we've got this graph G, and we've got these subgraphs, these two subgraphs that we are calling G prime. Why are they subgraphs? Like here we've got V2, V3, and V4 here. As you see here, we've got this subgraph of V3, V4. We've also this V2 is our subgraph. We've also this one, V1, V6, and V7 is also a subgraph. V1, V6, V7. You can actually take this one. It will be what? Your subgraph. Don't know if there is any question here. I think that will be the end of the introduction to graph theory. This will be the end.